In this video, we will explore the intriguing interplay between time, consciousness, and cosmology, focusing on bridging the gaps between these seemingly disparate concepts. In its current form, this research touches on deep themes that underlie theoretical physics, particularly the use of fractals as a conceptual model for connecting the subjective experience of time with broader cosmological and quantum frameworks. Fractals, mathematical objects characterized by self-similarity, repetition, and embedded dimensionality, provide a powerful model for understanding the fabric of time. A key feature of fractals is self-similarity, which resonates across scales from the largest cosmological structures to the smallest elements. This self-similarity suggests that time itself operates fractally, with repeating structures nested within each other. This concept is particularly relevant to the concept of periodicity in physical systems, where cycles repeat regularly. However, fractal time introduces complexity beyond simple periodicity. In contrast to linear or cyclic time, fractal time suggests scaling invariance, where temporal patterns exist simultaneously at multiple scales, not limited to uniform repetition, but manifest themselves in variations similar to the fractal geometries seen in nature. Critically, the iterative nature of fractals, where the outcome of each iteration feeds back into initial conditions, describes a fitting analogy for the progression of time. This feedback process is reminiscent of the irreversible nature of time discussed as entropy in thermodynamics. But within a fractal framework, this progression can allow for both local variation and global coherence. It is supported by a strikingly different interpretation of temporal flow, and by certain interpretations of quantum mechanics, such as the path integral formulation, in which all possible paths contribute to the outcome. Laurent, Nottale, has presented the fractal spacetime model as an entry point for reconciling fractal geometry with quantum mechanics. Nottale's work is based on the idea that spacetime itself can be fractal on quantum scales. This proposition is compatible with the non-differentiable ways assumed by Feynman's quantum path integral approach. Time becomes a dimension within a fractal spacetime, and its fractal nature can here explain certain features of quantum temporal reversibility, a property of quantum systems in which time evolution is symmetric. This means that time can theoretically flow backward. This concept suggests that under certain quantum conditions, the arrow of time may not be strictly one way. However, Nottale does not go into the subjective experience of this potential reversibility. Susie Vrobel's model extends the fractal interpretation of time into the realm of subjective experience, with Vrobel relating fractal structures to timelessness and the human perception of insight, inspired by Roger Penrose's concept of timeless moments of consciousness. While Nottale's model is mathematically rigorous, Vrobel's approach takes a more philosophical tone, suggesting that our subjective experience of time may not correspond with the objective flow of time as defined by physics. In moments of profound insight or altered consciousness, the fractal nature of time may allow for the perception of timelessness, where time does not progress linearly, but instead manifests itself as an intertwined, self-similar structure. This philosophical alignment with Penrose's quantum theory of consciousness, particularly with the non-computable processes occurring in the brain, offers a potential bridge between the qualitative experience of time and the quantitative models proposed by Nottale. One of the deep properties of fractals is the concept of the infinite within the finite. This stems from the capacity of fractals to exhibit infinitely complex structures in a finite space, as seen in the Mandelbrot set. The application of this concept to time is intriguing because within any finite moment, an infinite range of temporal scales and experiences may be embedded. This idea is considered in conjunction with the subjective perception of time, where moments of profound significance may feel infinitely vast, while other periods seem to pass unnoticed. In a cosmological context, this fractal property may also offer insights into the structure of the universe itself. If space-time is truly fractal, then the universe may contain self-similar structures at very different scales, from subatomic particles to galactic clusters, and time plays a similarly intertwined role. The argument for reintegrating consciousness and external reality in our models of time is quite important. Traditionally, physicists have sought to separate the subjective, consciousness, from the objective, external reality, to maintain clarity in their descriptions of the physical universe. However, time is a fundamental aspect of both consciousness and external reality, and any complete theory of time must account for their interrelationship. Theories such as John Wheeler's participatory universe or more recent explorations of the role of observers in quantum mechanics suggest that consciousness may not be a passive witness to the unfolding of time, but an active participant in shaping its structure. A fractal model of time with its self-similar and recursive properties offers a compelling framework for exploring this connection. In this context, fractals represent a way of capturing the concept of infinity within a finite boundary. This is a central theme in both mathematics and theoretical physics. In this video, we'll focus on how fractals exhibit self-similarity, the role of fractal dimensions, and the philosophical implications, particularly about time and space. Defined by their self-similarity, fractals have an inherently irregular structure that persists at every scale. This property ensures that no matter how closely you approach a fractal, smaller patterns mirror larger patterns, and each line breaks down into finer, iteratively generated lines. This recursive property of fractals speaks to the Hausdorff dimension, a measure of the complexity or density of the fractal. Unlike traditional Euclidean objects with integer dimensions, fractals often have non-integer dimensions, reflecting the intricate detail embedded within them at every scale. A classic example is the Mandelbrot set, a complex and infinitely detailed mathematical structure. But a simpler example is the Koch snowflake, which vividly illustrates the paradox of a shape with an infinite perimeter contained within a finite space. This paradox not only serves as a hallmark of fractal geometry, but also provides a concrete visualization of the concept of infinity. The Koch snowflake helps convey how fractals express the idea of infinity within finite boundaries. Starting with a simple geometric figure, such as the Star of David, each step in the iterative process adds smaller triangles to its edges. As this process continues ad infinitum, the shape's perimeter grows infinitely larger, even as the area remains finite. This process evokes the concept of infinity, which is deeply connected to our understanding of time. Time, like a fractal, confronts us with concepts of infinity, whether through the idea of infinity or through the subjective experience of timelessness within the finite present moment. This connection between fractals and infinity is particularly compelling when viewed through the lens of time. As James Gleick puts it, a fractal is a way of seeing infinity, providing a mathematical and visual representation of how infinite complexity can emerge from simple iterative rules. The fractal model, therefore, serves as a powerful analogy for the infinite nature of time that can be subjectively experienced in finite moments. In this way, fractals provide a framework for visualizing the infinite within the finite, similar to how we perceive moments that seem to stretch on forever as time slows down during intense experiences. We can also compare fractal self-similarity to the properties of holographic film. In a hologram, each piece of film contains information about the entire image, albeit at reduced resolution when viewed at smaller scales. This analogy captures a key property of fractals: cross-scale self-similarity. However, while the resolution of a hologram decreases when smaller portions of the image are examined, fractals retain clarity at all levels. This highlights the fractal's capacity to maintain structural integrity across scales, which is crucial to understanding its applications in physics. In holography, the concept of encoding the whole into each piece reflects how information is distributed in quantum systems. For example, in the black hole entropy described by the holographic principle. In this principle, the information content of a volume of space can be thought of as encoded in its boundary surface, like a hologram. Similarly, fractals encode an infinite amount of structural detail within a finite region. This insight is compatible with certain interpretations of quantum gravity and could have profound implications for how we understand space, time, and information at the most fundamental levels. The concept of fractal dimensions is important for understanding the true complexity of fractal objects. Traditional Euclidean dimensions, length, width, and height, are inadequate for describing the complexity of fractals. Instead, fractal objects have non-integer dimensions that reflect their degree of self-similarity and the density of their structure. For example, a Coke snowflake has a dimension between 1 and 2, indicating that it is more complex than a simple line, but less full than a two-dimensional surface. This discussion provides a broader perspective on how we understand space and objects. Dimensions are usually understood as the extension of an object along three Cartesian coordinates, x, y, z, but fractal dimensions challenge this simplicity. Fractals reveal that even within seemingly one- or two-dimensional objects, there can be complex, intertwined structures that are not fully captured by integer dimensions. For example, although words on a two-dimensional page may appear distinct from each other, we need to step into a higher third dimension to fully perceive the parts and unity of the page. In theoretical physics, this idea reflects the necessity of introducing higher dimensions to explain certain phenomena. For example, string theory posits the existence of additional spatial dimensions beyond the three known dimensions, allowing for a more complete description of the fundamental forces and particles in the universe. The idea that adding dimensions can solve previously unsolvable problems is a profound idea that is often seen in both mathematics and physics. This approach is well illustrated by the Pythagorean theorem. Here, the relationship between the lengths of the sides of a triangle, usually considered in one-dimensional terms, is a relationship between two-dimensional areas. The unknown length of the triangle becomes solvable by stepping into an additional dimension and considering areas instead of lengths. This principle of transcendence through dimensionality is common in theoretical physics. For example, higher dimensions play an important role in string theory, where the addition of extra spatial dimensions beyond the traditional three dimensions is necessary to unify the fundamental forces of nature. These dimensions, although not directly observable, provide solutions to problems that cannot be solved within the lower dimensional framework. Similarly, in mathematics, the concept of complex numbers, which extend the real number line onto a two-dimensional plane, enables the solution of equations that have no real number solutions. The continuum between time and timelessness can be considered a new dimension of scale. This suggests that time as we perceive it may emerge from the division of a primordial, timeless state. Each division of timelessness creates a finer granularity of time, and this expansion may be exponential. In this model, timelessness represents the undivided moment, while time represents the emergence of divisions within that moment. This idea is compatible with certain interpretations in quantum mechanics and cosmology, according to which time may not be a fundamental property of the universe, but rather an emergent phenomenon resulting from more fundamental, timeless laws. In some theories of quantum gravity, time may disappear at the smallest scales, but reappear as a macroscopic property of spacetime. It is possible to extend this idea by suggesting that the temporal scale, the continuum between time and timelessness, provides a dimension outside space-time through which we can perceive relations within space-time. This also aligns with the ideas in relativity that the nature of time is intertwined with space and that time perspectives change depending on the observer's frame of reference. The placement of timelessness within time, as discussed in philosophical and psychological studies, can also provide a framework for understanding subjective time. While fractals allow us to visualize infinity within finite boundaries, perhaps time, by its fractal nature, contains timelessness within its fabric, accessible through certain experiences or altered states of consciousness. Fractals have a special relationship to dimensionality because they exist in non-integer dimensions. Unlike traditional geometric objects, fractals do not conform to integer dimensions. For example, the Koch snowflake has approximately 1.26 dimensions, indicating that it is more complex than a one-dimensional line, but does not fill two-dimensional space. The Mandelbrot set, on the other hand, is an example of a curve that fills a two-dimensional plane, having two fractal and topological dimensions. This concept of fractional dimensions expands the traditional concept of dimension by allowing us to quantify the roughness, irregularity, or complexity of an object. For example, a Koch snowflake achieves its fractal dimension by adding triangular projections to each side of an equilateral triangle. As this process continues, the perimeter grows exponentially, creating a more complex shape that partially fills two-dimensional space, but does not become a completely two-dimensional object. The fractal dimension serves as a measure of how much of the next dimension the object occupies. The fractal dimension becomes particularly interesting when considered in the context of physical systems. Many phenomena in nature, such as coastlines, mountain ranges, and even clouds, exhibit fractal-like behavior. The degree of roughness or brokenness of a surface can be measured by its fractal dimension, providing insights into the underlying processes that shape it. As you travel deeper into a fractal, moving through smaller scales, the journey shifts from an external dimension to an internal dimension. This movement across scale is one of the fundamental properties of fractals. As you zoom in, the fractal reveals more detail, and its structure remains self-similar at every level. The fractal dimension remains constant across scales, distinguishing fractals from non-fractal objects, which tend to lose detail as they are magnified. This idea is supported by certain theories in cosmology and quantum mechanics that the fabric of spacetime can have a fractal structure at extremely small scales. In some models of quantum gravity, space-time is not smooth, but has a fractal-like structure that changes in dimensionality depending on the scale at which it is observed. This can explain certain phenomena, such as the apparent smoothness of space-time at macroscopic scales and its possible disorder at quantum scales. The Hausdorff dimension formula provides a way to measure the fractal dimension of a self-similar object. In the case of the Koch snowflake, the triangle's edge is divided into 3 pieces, and 4 copies of the original piece are created, yielding a fractal dimension of approximately 1.26. This calculation shows how fractal dimension captures the complexity of the object and its self-similarity at different scales. While the topological dimension of an object remains constant, a line is always one-dimensional, regardless of its complexity. The fractal dimension provides a measure of how much the object fills the next higher dimension. For example, a curved line has a topological dimension of 1, but because it curves in space, it requires a two-dimensional plane to exist. Therefore, its fractal dimension will be greater than 1, reflecting its additional complexity and roughness. This concept of fractal texture has important implications for understanding natural phenomena. In many systems, the roughness or irregularity of a surface, such as a mountain range or a coastline, can be described by its fractal dimension. One of the fundamental connections between fractals and time is the unpredictable rate of change that they both share. In fractal mathematics, functions are often non-differentiable, a property in which small changes in one variable can lead to unpredictable and highly irregular changes in another variable. This reflects how we perceive the passage of time. Sometimes it appears to move slowly, sometimes it feels fast, and sometimes it appears to stand still. The unpredictability of fractals reflects how time itself is experienced subjectively. Our perception of time can change depending on a variety of factors, such as emotional states, cognitive focus, or external conditions, just as the local irregularity of a fractal can change unpredictably when zoomed in on different scales. In this sense, fractals capture the nonlinear experience of time, which differs from the more regular and measurable passage of time marked by clocks. This aspect of fractals also ties into chaos theory, in which systems exhibit deterministic yet unpredictable behavior. Time, which is fundamentally governed by physical laws, often appears chaotic and unpredictable, especially when considering systems such as weather patterns or financial markets that are affected by fractal-like structures. Thus, the unpredictable nature of time can be likened to the behavior of a fractal function, which exhibits infinite complexity despite being generated by a simple set of rules. Consider a day as a smaller cycle within a larger cycle of a year, which is contained within larger cosmological cycles. Similarly, fractals exhibit self-similarity across scales, where structure at one level of magnification resembles structure at a smaller or larger scale. This makes fractals a natural model for the cyclical and repetitive nature of time, where each cycle reflects the larger structure of time, similar to the fractal repetitions seen in the Mandelbrot set or the Koch snowflake. This cyclical nature of time is also compatible with many philosophical and scientific models of time. In cosmology, the idea of cyclical time, in which the universe goes through endless cycles of expansion and contraction, is integrated into the fractal structure of patterns repeated at different scales. In human experience, life is marked by cycles such as seasons, biological rhythms, and historical repetitions, all of which can be seen as part of the fractal-like unfolding of time. Fractals are well known for their paradoxical relationship between infinity and finitude. A fractal, such as a Koch snowflake, has an infinite perimeter but encloses a finite space. This paradox is reflected in the way time is. A moment in time can be perceived as both finite and infinite. Finite in the sense that it is bounded by the past and the future, but also eternal in the sense that it is always the container of experience. Each present moment, although transient, contains within it the entirety of our conscious awareness at any given point, just as a fractal contains infinite complexity within a finite region. This paradox challenges traditional notions of time as linear and uniform. In the context of fractals, the infinite detail of a fractal structure suggests that within any finite time, there can be an infinite number of smaller, nested moments, just as there are infinitely many smaller scales within any finite fractal boundary. Furthermore, in theoretical physics, this concept of infinite complexity within finite boundaries is important in fields such as quantum mechanics and cosmology. The idea of a fractal-like time has implications for the study of quantum time, where the smooth passage of time on macroscopic scales is broken up into discrete, complex intervals at the quantum level, but instead varies with circumstances, emotions, and context. For example, during moments of intense focus or crisis, time can appear to stretch, allowing much more information to be perceived in a short period. On the other hand, during ordinary or routine activities, time can appear to collapse and pass unnoticed. This subjective variability of time is consistent with the fractal property of self-similarity at different scales. Just as zooming in on a fractal reveals greater complexity, focusing on the present moment can reveal greater depth in the experience of time, while broader views can soften these details. The fractal model also offers insights into the relationship between time and memory. Just as a fractal contains infinitely many smaller versions of itself, memory allows us to revisit past moments and effectively zoom in on specific points in time. The ability to access different temporal scales through memory and imagination suggests that our perception of time is inherently fractal, with each moment containing echoes of the past and the future. In summary, fractals offer a promising mathematical model for understanding time because they share many characteristics with the way time is experienced and conceptualized. Both fractals and time exhibit unpredictable rates of change, are constructed through intertwined loops, and have a paradoxical relationship between infinity and finitude. The fractal model of time opens up exciting possibilities for future research in both theoretical physics and cognitive science, suggesting that time may not be as linear or uniform as traditionally thought. Instead, it can be self-similar, complex, and layered, with each moment containing an infinite array of possibilities, just as each iteration of a fractal reveals new levels of structure. Thanks for listening, and take care.